Hello once again, class, and welcome to another mock lecture. Today we are going to be tackling implicit differentiation, so let's get to it. First, we need to talk about how most functions that we've dealt with up to this point in your mathematical career have probably been defined explicitly. Things like y is equal to x cosine x, y is equal to x cubed tangent of x squared minus pi x, and y is equal to the sine squared of x over x plus 1. These are all explicit because their general form is some y is equal to, and then a function that's in terms of x. But sometimes it's easier to write functions in an implicit way. And when something's written implicitly, y is not clearly defined, right? It's not clearly written as a function that's in terms of x, though sometimes you can solve for it and isolate it and make it look like something that's explicitly defined as opposed to implicitly. But instead, it's implied that y is just a separate function of x. And that's exactly how we're going to treat it moving forward. But what do they look like? Well, here's three examples. X cubed y is equal to 12 is an implicitly defined function. The sine of xy is equal to y squared is also implicitly defined. X squared plus y squared is equal to 25 is implicitly defined. And the thing is, just like we said before, y we're going to treat as some entirely different function in terms of x. So y is like its own f of x or g of x or h of x or something. It's some function in terms of x, but we're just writing it as a y. But we are able to think about it as a function of x. Now this is very much, it kind of goes against the way that you've been writing functions, probably since you learned what a function is. So you might be wondering, how is this useful? Why is it useful to write functions in this sort of manner? And it's because oftentimes implicitly defined functions are actually defining more than one function in a single equation. For example, x squared plus y squared is equal to 25. If you solve for y, right? If you actually get y by itself, you have to subtract x squared from both sides, and then you have to take the square root of both sides. And when you do that, right, whenever you introduce a square root to an equation, you have to consider both the positive and negative results of that square root. And so this one equation, x squared plus y squared is equal to 25, is really defining two different square root functions. The negative one is this kind of curve below the x-axis. The positive one is this curve above the x-axis, and really what you're doing is this one function is defining a circle centered at the origin with a radius of 5. Right? The radius of this circle is 5. And we're able to do this with just a single function as opposed to saying, oh, well, let's have two different equations. Now, of course, you might also say, well, hold on a sec, Mark, that's not a function. It fails the vertical line test. And okay, that's a fair point. But really, again, this is defining more than one function at a single time. And that's why it's more convenient. Now, how do we do implicit differentiation then? Well, basically, if a function is defined implicitly, the implicit differentiation is just finding the derivative of that particular function. And I think the easiest way to define this, the easiest way to explain how to do implicit differentiation is actually just to go through an example. So let's do some examples. All right, example number 1. Let's just take the derivative of this circle, centered at the origin with a radius of 5. X squared plus y squared is equal to 25. Now, this is super cool. I love implicit differentiation. Here's how this works. First, we're going to apply just basic derivative laws to this thing, right? So we're taking the derivative of the left-hand side and we're taking the derivative of the right-hand side. The left-hand side is just a sum of two terms, so we get to apply the sum rule for derivatives, right? So the derivative of x squared, that's pretty easy. This one I'm going to say for last, and then that's just 0. So let's just get those out the way. By power rule, derivative of x squared is just 2x. By constant multiple, or derivative of constant rule, the derivative of 25 is just 0. It's this thing, right, that we are not 100% sure how to deal with. But what you have to remember is that this thing, this y, is a function of x. It is like an f of x. And that function is being squared, which means it's a chain rule application. So in this situation, y is our u, right? Our du dx is just dy dx, and arguably, kind of talking out loud, I'm not sure what the point of doing this was, I guess really just to showcase that, hey, I'm using the chain rule, and typically u is what we're using for that. The outer function, the f function, in terms of u is u squared, and then the derivative, d dx of f of u is equal to 2u. Okay, so the chain rule dictates that this just becomes 2u, which is just 2 times y, times the derivative of the inner function, which is y, right? So we get this, 2u times du dx, which is 2y times dy dx. So that's the derivative of y squared. It's an application of the chain rule. It's almost like you're just taking the derivative of this as if it's an x, but then you're multiplying by a dy dx. That's actually kind of a legitimate blanket statement, but we'll get more into that a little bit later. Anyway, by the chain rule / implicit differentiation, and that's the new part, right? That's the part that we're talking about for today. We get this as the derivative of y squared with respect to x. Now, of course, we're trying to find y prime. We're trying to find dy dx when we're taking the derivative of this thing, so we'd like to get it so that our derivative is only in terms of x. So we have to solve for dy dx. Isolate this to find our derivative. This is just some algebra to get down to the point where you know that dy dx is equal to negative x over y, right? And that thing is going to be the slope for really both of the functions that are defined by x squared plus y squared is equal to 25, which means that this can be used to find tangent lines of that circle, right? Of the circle thing that we saw before, right? Of this. As long as you know a point, some xy. Man, that's a really good circle. Now, you might be wondering, why do we even need to learn how to do this, right? Because, we already know that you could just get this thing in terms of y, right? We could just get y by itself, take the derivative. The plus minus actually goes away here when we replace this thing with y, because y is taking the place of the plus minus, so it kind of takes care of that to make it 2y. And so, okay, we get down to the same thing. So, again, why do we even need to know how to do implicit differentiation? And the answer to that is sometimes it's really difficult to isolate y. Consider the sine of xy is equal to y squared, and I said, let's take the derivative of this. Let's find y prime. How do you even do that for this function, right? You might be tempted to say, oh, we got to free up this y so that we can take the derivative of that thing. But in doing so, you'd have to take the sine inverse of both sides, right? Sine inverse and sine undo each other. But then now you have y trapped inside of a sine inverse function. So pick your poison. Do you want y inside of a sine function, or do you want it inside of an arcsine function? Either way, how are we going to get y isolated so that we can just take y prime? That's why we need to know how to do this implicit differentiation stuff. This function is defining more than one function with one equation. It's defining like this whole family of functions. The graph looks insane. Look at this thing. It's definitely on its own, it's not a function, but if you were to isolate y, you'd find that it's really defining a whole bunch of different functions. And so by implicitly differentiating this thing, we're going to be able to find the slope of all of this stuff, given a point, right? We always need a point xy if we're going to find a slope. But so anyway, the point is we have to use implicit differentiation to find the slope of this curve. So when we do that, we take the derivative of the left with respect to x, you take the derivative of the right with respect to x. We've already done the derivative on the right, actually. It was the last example we just did. We get 2y times dy dx. On the left, let's think about this, right? This is a chain rule situation, right? The outer function is sine, and then it kind of looks like there might be product rule stuff, but let's take it one step at a time here. Chain rule says you got to take the derivative of the outer function. The derivative of sine is the cosine of whatever the inner function is, which is just xy, and that's why I have this. But per the chain rule, now we're going to multiply by the derivative of x times y, which indeed is a product rule derivative. So this, by the product rule, because remember, y is a function of x. It's like g of x or f of x. It's like some other function in terms of x. It could be like a cosine function. Right, we're going to treat it the same way. Inside that parenthetical there, we get the derivative of x times y plus the derivative of y times x. That's just the product rules definition. And so the derivative of x is 1. So we get y plus the derivative of y which is one time, that's chain rule. Then we have to take the derivative of y, which is just dy dx. That's where the dy dx comes from. I kind of switched the order of these things, and I can do that because multiplication is commutative, but it is kind of weird that I chose to do that there. Nothing has happened on the right so far. But then again, we want to isolate the dy dx, right? Right now it's on two different parts of our equation, and so we're going to have to combine them somehow. Luckily, we can free this up with some distribution. So what I did is I distributed the cosine xy to get this stuff. Now the dy dx can be moved around. It does have all this other stuff kind of that has to go with it, but we can still do it. So I'm going to go ahead and I'm going to subtract the x dy dx cosine xy from both sides to cancel it here and then have it be subtracted on to this side. And then I'm going to notice, well, look, these two things have a dy dx in common. So let's factor it out. And then I'm trying to get this by itself. So let's just divide both sides by this 2 minus x cosine xy stuff to cancel that. And whatever I do to one side, I got to do to the other side. So here you go. Here's the derivative. Y cosine xy divided by 2 minus the cosine of xy. By the way, we've been doing this all in Leibniz notation, but I just want to let you know that you could do it in Lagrange notation if you wanted to. You could have the y prime stuff, and then if we take a second derivative, like in our next example, spoiler alert, we'll have y double prime. But you could, either notation is fine. I find myself kind of going back and forth all the time. So let's do one more. In the last one, we have x to the fourth plus y to the fourth is equal to 16, which is a pretty cool looking graph. You should go to Desmos, actually. Pause it here, go to Desmos and graph this thing. But anyway, we want to find y double prime. So we want to find the second derivative of this thing. Well, let's just start by differentiating with respect to x on the left and on the right. Nice thing is the derivative of 16 is just 0. On the left here, this is just power rule stuff. X to the fourth becomes 4x cubed. This is chain rule, right? That's implicit differentiation. So we got 4y cubed and then times the y prime. We're looking for y double prime, so we should differentiate again. Now, what I actually did is I got y prime by itself so that when I differentiate this thing, it'll be in terms of y double prime. Like this just becomes y double prime, and then I just have to worry about implicitly differentiating this thing here. So that's what I did. You could just differentiate here at this stage and then solve for y double prime, right? Just know that that's the thing that's going to become y double prime. But yeah, I chose to find y prime first, and there's actually a reason I chose to find it first, which I'll explain when we get to that point. But either way is a viable way to find the second derivative. So here I differentiated again because I want to find the second derivative, and then so I just nicely just get y double prime by itself. I don't have to solve for it. This is it, right? This is y double prime. Now, I did simplify a little bit. I knew y prime, for example, is x cubed over y cubed times -1. It's negative x cubed over y cubed. So I went ahead and did that substitution. I'm just trying to simplify kind of at this point. A couple things happened here. The first thing that happened is this is really over 1, so I just multiplied these things straight across. When you have y squared divided by y cubed, that's 1 over y, but I chose to write it as y to the -1, which I like a little bit better. To continue to simplify this thing even more, actually, I factored out the commonalities. They both had a 3x squared in it, right? This one has definitely more than an x squared in it. But then I also took out a y to the -1. And the reason I did that is because I wanted to factor this thing out. But if you factor out a y to the -1 from y cubed, the power for y actually will increase in that case. And I did this because we know what y to the fourth plus x to the fourth is. It's just 16. So we can simplify this thing a lot by just replacing the y to the fourth plus x to the fourth with just 16. And so we get -48x squared over y to the 7th is our second derivative, right? This thing is describing the concavity of this thing because it's the second derivative. Now, I could do a whole lot more examples. I love doing implicit differentiation. I could implicitly differentiate all day, right? If there was a job where I could just implicitly differentiate from, 9 to 5, I would do that job. That sounds awesome. But we'll stop here. I think that's enough examples. We saw really two where we're using Leibniz notation, and then we used a little bit of Lagrange notation as well. So I think I've covered my bases pretty well. Main thing to keep in mind is you can differentiate y with respect to x, and it just requires the chain rule, right? When you do that, y is a function in terms of x. That's what you got to remember. All right, so hopefully you guys learned something. If you have any questions, leave a comment below or send me an email. Thanks a ton for watching, and I'll see you in the next one.